Okay. So what we do is today we'll deal one of the important problems for the mechanical engineers, and that's called sequencing. And in previous cases, we talked about the linear programming, the transportation problem, and followed by the crashing network methods, network analysis, critical path method, PERT, then crashing. And this is kind of a sequencing. Sequencing in the sense, like if, for example, to manufacture what do you call a two-wheeler, first is raw material processing, then they do what do you call fabrication, then they do assembly, then they do finishing, and they do packing, or they send it with the finished product. Or if it is a two-wheeler or automobile, then they do a test drive to satisfy the quality check and all. So similarly, if we have two machines to do a particular job. Say for example, lathe machines, like in a factory, it has got number of lathes. Say for example, the first thing we'll consider two machines, and there are five jobs. Five jobs in the sense like five pieces of machining or something like that. But we have got two machines. We need to properly sequence them in order of their decreasing time, or in the order of their minimum time. For example, these are the hours required for that particular process. For example, job one requires 5 hours or 5 minutes or whatever might be, 5 units in for machine A, whereas it requires 2 units for machine B. And whereas job 2, it requires 1 units for machine A and 6 units for machine B, and so on. Okay. So now the first step is, and they say order is AB. So we need to only progress A to B. Sometimes in a problem, we might also give B to A. So, or if you have a multiple machines like ABC, then we can even say CAB, ACB, or ABC, whatever might be the order. So that gets varied. In today's class, we talk about n jobs in two machines. Only two machines. We have got n number of finite jobs. So that is the basic idea. So what we do is, in the first iteration, we'll take that particular thing and we'll, hello, hello. Is there any questions? Okay then.
No, sir.
So first iteration will be taking that problem, and we will see, and we will make this particular thing. So we can allocate only five jobs in sequence. Say for example, we'll find out which job has the minimum duration. So this, and also one assumption is that this is all individual jobs and doesn't have any prerequisite or dependencies. So it can be done individually. So that is one assumption we will do for sequencing. We will make a column like this: machine A this side and machine B this side, and we have got five jobs: one, two, three, four, five columns, and then we look into the overall picture and find out which has the minimum time in overall matrix. Remember, in the least cost method of transportation problem, we talked about the cell that has got the minimum transportation cost. Similarly, we look into the area, then we will find out, and one is the minimum time, and that corresponds to job 2 of machine A. So which means that we will put machine A. Besides that, the first thing which we're going to do is job 2. Job 2 will be here. Then once you finish that, you cannot take machine B because that job is assigned to machine A. So we will be deleting this row. So that is why I marked it in a black color. Next, among the remaining thing, we'll find out which has the minimum time. In this case, it happens to be job 1, number 2, 2 hours, and it's for machine B. So which means that then we will be taking this particular thing and we'll be assigning it to machine B. So you can see that since the order is A to B, we'll be having machine A left and machine A right. And if it is BA, then the machine B will be here and machine A will be here. So which means that we will be, it is just like two guys working in a factory. So if one guy go for a lunch, then another guy will do. Then the guy who went for lunch come back and this guy go for lunch. So that is how it is assigned or in a sequence. Okay. Then once it is done, J1, so we'll completely eliminate this column, and the remaining column is this J3, J4, and J5. And among this, the minimum is 3. that corresponds to machine A of job 4. So which means that we'll have J4 machine A. Then we will eliminate this, and the remaining is J3 and J5. So the least one will be in J5, that is 4, that corresponds to machine B. So we will put J5 here and we'll fill this, and the remaining is the same, and 9 or 7 it is machine B, then it is 7 or J3. So this will be in a sequence. So which means that first we'll perform J2, J4, J3, J5 and the job J1. So that is what we generally found out the sequencing. Okay. Then one important thing is we need to find out the in time, out time. Then we also, very important term is idle time. Is that machine ideal for long or something like that? Or how much time is a machine got ideal or something like that? Okay. So we have taken this particular table, the question. Then what exactly we have found out is in machine, this is the problem of machine A to machine B. So which means that in time 1, so 0 time, the machine A can start at no waiting time. So it can directly start at 0 time. You remember in critical path method, we have got the earliest event time for the initial activity we have taken as 0. Same way, this has to be 0. And we'll go to J2 in the table and see what is the actual duration of the J2 of machine A. So the actual duration is 1 hour. So 0 plus 1 is 1. So the time out will be 1. Okay. Then the timeout will be the time in for the job number 4. Okay, so we'll put that 1 here. And job number 4 of machine A is 3 hours. So which means that 1 plus 3 will give us 4. Okay. And absolutely there's no waiting time for machine A because machine A is the predominant or equipment to do. Then we'll come back to this J3 and it ends at 4 hours. Timeout is 4 and it can be starting at that particular 4. I mean, this is 4.1 hour and so on. Then J3 in the table is 9. So which means 4 plus 9 is 13. Then similarly, put that 13 in J5 and find out what is J5 duration in this particular table. It is nothing but 13 plus 10 is 23. Okay. So 23, I will be here. Then J1, the last activity. J1 is 5 hours. So 23 plus 5 is 28. So this is regarding the machine A. This has no problem in finding out the in time and out time. But the problem of machine B is a dependent machine. So it cannot perform when the machine A is performing. Okay. So which means that the time in for machine is 1 hour. So which means that the first instance, the machine B will wait till the machine A is getting over. So in that case, the machine A gets over by 1 hour. So it has to wait 1 hour, then only it can start. So the starting time of a machine B is 1 hour. So since it has to wait 1 hour of machine A, so the delay of the delay or the ideal time for machine B is 1 hour. Since it has to wait from 0 to 1 hour, so the ideal time for machine B is 1 hour. And what is the duration for machine job to machine B is 6. So which means that 1 plus 6 is 7. So this is regarding the time allocation for machine B. Yes.
So will machine B always be dependent on machine A? I mean, in
That
such
is
question.
that is the question. No, we have taken order of AB. If we have taken an order of BA, then probably we can start machine B and machine A will be dependent. Or sometimes they say no order. No order
Yeah.
in the sense they can do simultaneously. Then you don't have to wait for this. You can even start at 0.
Okay, so for that, it will be mentioned in the question that they are
Yeah.
independent.
Yeah, but if it is independent, then there is no problem of sequencing. This entire problem is we are finding a perfect sequence.
Okay, sir.
If both are doing it simultaneously or parallelly, then there's no question of sequencing. So we can assign any job for any machine at any point of time, right?
Okay, sir.
So that is the logic. Okay, fine. And then what happens is then this 7 has to be put here. So but when there is a when you put it for machine B, you should make sure that this number is lesser than this number. You know, if supposing you have the ideal time for, I mean, the out time for job number 2 is 2, say for example 2. Say 1 plus 2 will give us 3. You cannot put 3 because the job 1, I mean, job 4 of machine 4 completes only by 4th hour. So which means that you cannot start early. So you have to wait till that hour. We have to put it 4 here. Then we have to put an idle time of 1 hour. So since we have got the 3, but in this case, luckily we have got the timeout to be 7, which is well ahead of the 4th hour. So which means that we'll put directly here 7th hour. Then job 4 of machine 2 is 8 hours. So 7 plus 8 is 15. Okay. Then we can substitute directly 15 here. The reason is that 13 is less than 15. Okay. So which means the logic is we are waiting for the machine A to perform. Then only we have to perform in machine B. Okay. In this case also, luckily we have got the value what do you call, greater than or equal to this particular thing. So in this case is 15, which is greater than 13, and 15, and job 3 of machine B is 7. So 15 plus 7 is 22. Okay. Then look at here. This is very important. We end up in 22, but we don't put here as 22. You know why? Because the job 5 of machine A gets over only by 23. So which means that we cannot put in 22. So we have put a value called 23. When you put a value called 23, which means you are waiting for 1 hour, and that 1 hour will be your idle time for machine B. Okay. Then very importantly, 20 this thing 23 plus 4, I guess. I think it's job 5 is 4, which is 27. But A4 gets only completed by 28. So we have to wait 1 hour. So 28 minus 27 is 1. So we have to wait 1 hour. So that 1 hour is put in here. It could be any time. Say for example, in this case, it's just idle time be 1 hour. In some problems, you might get out 4 hours for a one idle time, one iteration idle time, then 3 hours and 2 hours, depending upon the difference in the machine A terminology. We will have this particular time, what do you call, the ideal times. And finally 28, this is the 28 for finishing of machine A, and 28 will be the incoming time for machine B. Then for J1 it is 2 hours, then 28 plus 2 is 30. This 30 I marked in blue color, which means that is 30 is a elapsed time. Very importantly, if a problem asks what do you mean, what does elapsed time, or calculate the elapsed time, this is the elapsed time. This 30 hours is the total machining time for both using machine A and machine B. So this is the total time in sequence. So the elapsed time is 30. The elapsed time minus the final timeout of machine A will be the ideal time for machine A. So machine A has finished its job. Then the entire process is for 30 hours. So the 2 hours the machine A will be idle. So that is why we have given 2 hours for machine A. So that is nothing but 30 minus 28. So, this is just like in a 3-hour exam. If you finish it by 1.5 hours or 2 hours, then you will be sitting idle for another 1 hour or 1.5 hours or even half an hour. That is what basically the idle time for machine A. So this is the overall time or elapsed time. That minus the time out of the machine A will be the idle time for machine A. And if you compute the overall idle time of machine A is just 2 hours, and idle time for machine B is 3 hours. Okay, so this is the basic or the optimum idle time. But if you try this job sequence by J1, J2, J3, J4, you will get a lot of ideal times. So this is kind of an optimized procedure for performing the sequencing. Okay, so I'll just upload this slide. So there's another example also I made using n jobs and 2 machines. Similarly, there is a model called 3 machines and n number of jobs, and n number of jobs and m machine or k machine. So which means that ultimate infinite number of machines and finite number of what you call jobs. So that we will be doing. So in tomorrow we'll be trying finishing the sequencing, and we'll start the inventory model. Okay, so I think we have come to the end of this lecture.